Okay, there were a couple of topics that we didn't quite have time for last time that I want to finish up, so this is stuff from the old notes, just a couple slides worth, and then we'll get into some new material. So the theme for today continues to be discrete time signals. And last time we looked at some particular discrete time signals and some kind of standard signals, unit steps, unit sample sequences, ramp functions, sinc functions. Today we're going to focus more on the periodic sort of signal, but there's some properties around that unit impulse sequence that are going to be very powerful for us, and just as they were in continuous time systems, they're going to be the basis of some of the mathematical simplifications that we do, and so worth clearing up and understanding at the outset. So these are properties of the unit impulse sequence. Remember, that was the sequence that's just 0 everywhere, except at one particular sample it has a value of 1. I don't even have to show it in parentheses, it's a value of 1. And that would be a delta of n sequence. If I shifted that over, this is our n index, if I shifted that over here to 2, made that 0, well, that's a delta of n minus 2, a shifted unit sample sequence. Again, the characteristic of the sequence is it only has one non-zero value, and that non-zero value is a 1, unless I put some multiplier out in front, like 3 delta of n minus 2 would be something with a height of 3. But it's still only a single sample that's non-zero. Well, that weird sequence has a number of interesting properties. First is the product property, which says if I give me some other discrete time sequence x of n, whatever shape it has, if I multiply that sequence by a unit sample sequence, maybe even a shifted unit sample sequence, the resulting sequence is also going to be a unit sample sequence because all these zeros are going to cancel all the other samples. So that's kind of intuitive. I'll get a unit sample sequence. I won't get the same unit sample sequence because the one unit sample value is going to get multiplied by the original signal's sample value at that particular index n. And so I get a weighted unit sample sequence. And that's all I get. It's still a unit sample sequence. It's still shifted to the same position. I just end up scaling it. So I kind of pull out a value from that original sequence and have used it to scale my unit sample sequence. Mathematically, we'd say if you multiplied an x of n, a continuous time sequence, and this is one that has lots of non-zero values, by a shifted unit sample sequence, shifted by k, what comes out, it's equivalent to that original sequence scaled by x, but only at one index, the k index that my delta sequence was non-zero, and so we can drop this whole continuous sequence, or not continuous, this multiple valued non-zero sequence, and replace it with a single value. Kind of simplify that expression. Now that looks like a lot of mathematical gobbledygook, but that'll actually kind of help us as we're simplifying some things. A related property, well, there was a similar property in discrete time signals. It just had the same thing with continuous functions. So this is the discrete time version of that same product property for impulse functions. And like in continuous time systems, we also have a sifting property, which has a lot of words, which all basically boil down to the same thing. Take a general discrete time sequence, multiply it by a unit sample sequence, even one that's shifted, same thing, but now do one more thing. Now add up all of the sample values in the result, sum those together, and what you get is this original sample value of the original sequence that happened at the time of the non-zero sample of the unit impulse sequence. So mathematically, if I sum up the original signal multiplied by a shifted unit sample sequence, I get just the one value of this original sequence that happened at my shifted location. So give me a summation formula like that, If it's got a shifted delta in it, boom, it all goes away and gives me just a single numeric value. So it's like we pulled out one sample value out of this function by multiplying it by a unit sample sequence and adding up the result. And that, again, has a continuous time equivalent, the shifting property, which uses an integral to achieve the same thing. Yeah?
How is it different from the product property that you showed?
So the product property only went up this far, created this sequence.
Yeah.
What I did to the shifting property now is say, let me add up this, let me sum that sequence, sum those values. The result of that summation is going to be a single value that came from this original sequence. Yeah. So what's the point? So why do we care? Because this sort of summation is going to show up in some of the derivations we do, and we will be able to drop all this stuff and say just that. Okay. So it's going to be a bridge to simplification we'll be able to do in the future. Shifting property, it used to be the shifting property of delta of impulse sequences. Now it's the shifting property of unit sample sequences. All right. Now this is what you may have encountered if you started the homework. We said, here's a signal, express it as an array form, which means give me its individual numeric sample values, and represent it as a weighted sum of impulse sequences, of unit sample sequences. Well, what this is basically saying is you give me any arbitrary waveform, any discrete time signal, and I can represent that as a sum of unit sample sequences. This sequence would be, well, this sample value multiplied by a unit sample, a shifted unit sample sequence, and this value multiplied by another unit sample sequence, and this one and this one. I can add up a whole bunch of unit sample sequences to get this guy back. It's like you're decomposing this into a one sample at a time collection of sequences. Mathematically, it looks like this. Our original sequence is a sum of kind of the backwards of what the shifting property we just had. The shifted out version, a whole sum of those, a whole bunch of those. So take the x of -1 value, multiply it by a shifted unit sample sequence that has a non-zero value there, and that gets me that sample. And take the x0 sample and multiply it by a delta of n sequence, and that gives me that sample, as long as I add these all up vertically. Good question for that would be why? We just took a simple signal and broke it up into an infinite number of additional sequences. That doesn't sound very good. Well, it's kind of walking us ever so gently towards our favorite topic of time domain analysis, convolution. So that's on the horizon, and it's going to use that mathematical formulation in order to derive the discrete time version of convolution. But at least conceptually it should be okay with us, should be making sense. It seems trivial, but nothing scary there. Okay. All right, that's what we needed to catch up with. If there's not any questions on that, we'll get on to periodic signals. Oops, try that one. Okay. So more discrete time signals, but now we need to look at the periodic ones and start talking about what happens when I sample them and what happens to their periodicity. And short answer is, very strange things could happen if you do not sample properly. So we're not going to get to how you sample properly, but we're going to set the problem up here, and you're going to see the basis for what could go wrong today. Again, we're assuming we've got a real-world continuous time kind of signal, x of t, that we're going to sample every t sub s seconds. We call that uniform sampling, meaning I use the same time interval between all my samples. I don't change that. I have the same spacing. And we come up with a discrete time signal that is the values of the original continuous time signal, but I'm only using particular time arguments, ones that are integer multiples of that sampling period, and t sub s, where t sub s is the sampling interval, seconds per sample, would be its units, and is an integer index. So we're doing integer multiples of the sampling rate. That tells us the time. And when we make it a discrete time signal, though n This integer index becomes our horizontal axis. If I take the reciprocal of that t sub s sampling interval, I get what I call the sampling rate or sampling frequency, which has units of samples per second. All right. So far, nothing too scary. Here's a periodic signal. Looks periodic, and I take some samples of it, and we're going to start asking ourselves today, when I sample a periodic signal, do I get a periodic set of samples or not? And by a periodic discrete time signal, we mean the discrete time sample values have to meet this definition, that if I stop anywhere along here, I have to be able to advance some number of samples that we call the period, capital N, and get exactly the same value back, here. So there's a period, and every time I advance along, I should be able to get exactly the same values. So when I advance by an integer number of periods, I get the same answer. I can go 1 period ahead or 2 periods ahead. So k we assume is an integer. N is also an integer number of samples, where n is the discrete time period. And those sample values have to repeat exactly. Then we say we have a periodic discrete time signal. So far, not too scary. Capital N then is the period. It would be considered samples per period, or samples per cycle, if you like. And capital N has to be an integer in order for us to have a periodic discrete signal. I can't need to go ahead 2.5 samples to get a repeating pattern, because it won't repeat then. All right. Here's an example your book gives of a periodic function, the periodic rectangle function. We would define one period as where does the repeating pattern start and stop. If I can define that as an integer number of samples, it's a periodic signal. Similarly, here's one there where we've sampled a sinusoid, and even putting a gap in between, that's fine. I can still define a set of signals, even though the pattern changes in the middle, and that pattern repeats exactly, so still a periodic signal. No problem there. Now, sometimes things don't go as planned. And so today we're going to look at how can I sample a continuous time periodic signal, and the result get a periodically repeating set of discrete time samples. Is this a periodic signal? Pure cosine. Completely periodic. All right. If I sample it every t sub s seconds, t sub s, t sub s, t sub s, t sub s, or at a sampling rate 1 over t sub s, the discrete time version of that will have samples that, well, I replace t with nt sub s. That's the only times I get samples. Right? And I could probably even keep theta the same down here. I'm not going to necessarily change the phase. But we're going to rearrange this nomenclature a little bit. So this replaced the time argument, nt sub s. I know t sub s's reciprocal is the sampling rate, f sub s. So this, going from this point to this point, is not changing the expression at all. Why I want to do that is, well, don't worry, I didn't lose the n. Now I'm going to look at this combination, f0 over fs, and give it its own name, capital F. And I have now the standard form for a discrete time cosine signal, cosine 2 pi n capital F plus phase. All right, and if I'd had an amplitude multiplier, we would still have that out in front. It's still discrete time. N still has integer values, but F now is a frequency of sorts. In fact, we call that the digital frequency. And it relates to the original analog or harmonic frequency of the waveform that I sampled. It's that analog frequency divided by the sampling rate. That's how we defined it here. This is going to be the new frequency variable, frequency perspective of our discrete time signals. Now again, we've thrown away time here. We're in a sampled world now. And so what are the units of this digital frequency? Well, you can think of it as the analog frequency normalized by the sampling rate. So it's like fractions of the sampling rate. And if the analog frequency is in hertz, cycles per second, and we're dividing it by samples per second, that means it has units cycles per sample. So if I have a signal that has a 0.1 digital frequency, I get 1/10 of a cycle every time I go one sample ahead. So I must need 10 samples to get one cycle, yeah.
So you pretty much would never want this digital frequency to equal 1.
Pretty much say again?
You wouldn't want that digital frequency to ever equal 1.
You don't want that digital frequency to ever be 1. That's a rather bold statement. I think I could conceive of that. It's okay with me, but I'm probably not going to see that very often, and we're going to see why in a minute. But you're onto something. When I start normalizing things, it's trying to get a little tricky here. I got to worry about some boundaries. Everybody okay with the units? Everybody okay with the concept? It's digital frequency cycles per sample. Okay. Oh, by the way, if you like omegas, in the continuous time signal, we have a discrete time version, capital omega, the digital radian frequency, which is just the continuous time radian frequency omega divided by the sampling rate as well. And so if this is radians per second, this is samples per second, this capital omega has units radians per sample. And a lot of textbooks use the capital omega for digital frequency, because they like Fourier transforms in terms of omegas, and so this is common. I like to stick to the hertz kind, and cycles per sample has a little bit more physical meaning to me. So we'll use that mostly, but be aware there is this other construct which is just 2 pi times. Okay, let's connect the dots. I think you're onto something here. Let's see how these different frequency values kind of line up. And let's start in the real world with analog frequency. So I have a cosine. Right, a cosine would have a frequency spectrum of an impulse at plus or minus its fundamental its harmonic frequency. So we're in that kind of Fourier view of the world with positive and negative frequency. Now, if I sample that signal and bring it into the discrete time domain, then what does that axis look like? Well, we're going to normalize the analog frequency by Fs. So what was Fs before is now 1. And whatever was Fs over 2, half the sampling rate, that's now digital frequency 1/2, and so on and so on and so on. Now, once we get in this discrete time frequency domain, it's okay to talk about frequencies that are bigger than the sampling rate. They're kind of out there. But I'm actually going to be able to limit myself to a smaller subset of these and keep track of what goes on there, and then surmise what's going on everywhere else. So it's going to be unnecessary to talk about what's going on out here, because I'm going to know all the information from a small region inside. Haven't explained why yet, but that's the way it's going to be. Radian frequencies, obviously we take these guys up here, the analog ones, excuse me, multiply by 2 pi. So this would be 2 pi Fs. This would be just pi times Fs. And in that capital radian frequency, we normalize out the Fs's. So this has a radian frequency, capital delta of pi, 2 pi, 3 pi, and so on. So that's how these all kind of overlap. If we're talking about a particular frequency in the continuous domain and then sample it, where does it show up in the discrete time domain? And we're sticking to the same place horizontally there. Now, this range right in the middle, from digital frequency -1/2 to +1/2, or in analog world, half the sampling rate on the negative side to half the sampling rate on the positive side. We give that a special name. We call that the principal range. That's principal, AL, not LE. And why we call it that is because in that zone, if you tell me what's going on in this zone with my sampled signals and my discrete time systems, you tell me everything I need to know. Because what's going on over here and over here and over here and over here and over here, I can infer from what's going on in here. Because it's periodic. Because so we'll get there. We'll get there. But for now, nomenclature, naming, principal range, plus and minus 1/2 the sampling rate. Okay. -1/2 less than capital F, less than plus F. And again, F is in cycles per sample. Cycles per sample. Okay. Oh, 4:30, it's warm in here. It's Wednesday. We're starting to lose it. This is getting kind of boring. Let's convert some signals. Let's take a analog signal and let's make it a discrete time signal. Let's see what comes out. Here's a continuous time signal. It's got a continuous time argument. It's 2 times cosine 40 pi t. I'm going to sample it at 100 hertz. Oh, whoops, by the way, sorry. Some books use capital S for your sampling rate. Some do F sub S. They're the same. So that's S is the sampling rate, sometimes called Fs. So we're sampling this signal at 100 hertz. Riddle me this, Batman. What frequency is that? What continuous time, hertzy kind of frequency is that cosine? How many? 20 hertz. How did you figure that out? Right. The argument's got to be 2 pi ft. 2 pi ft is 40 pi t. Cancel out. You figure out f0 must be 20 hertz. All right. I'm going to take a 20 hertz signal. I'm going to sample it at 100 hertz. The digital frequency we get is what? Well, we take the analog frequency, we divide it by the sampling rate, 20 divided by 100, and we get 0.2. 0.2 cycles per sample, which means one cycle must take 5 samples, right? Okay. Our discrete time signal then has the form, well, still scale 2, cosine 2 pi n times capital F, 2 pi n times 0.2, or simplified cosine 0.4 pi n. That's how we'll write it in discrete time. And I guess, broke my nomenclature. I probably should have square brackets on these guys, because this is a discrete signal. Sorry about that. I'll fix the slide. Okay. Now, what could possibly go wrong? Let's look at some unexpected effects of sampling. Here's our continuous time signal, and we said that is periodic, right? Always. Always, always, always. If I sample this signal, is the sampled version periodic? Is that one periodic? That looks okay. But that's not always going to be the case. There's a differently sampled signal that does not, it's the same original signal, but these samples don't repeat. There's no repeating pattern in there, at least as far as I can see, maybe. And now we want to find out, question.
Wouldn't it inevitably have to repeat at some point? Right?
Would it inevitably have to repeat at some point? Actually, no. It doesn't have to. It often will, but now there's going to be a relationship between my sampling rate and my original frequency that I have to uphold in order to get a periodic answer. So let's look at that. Without looking at your notes and just thinking intuitively, can you think of a relationship between the sampling frequency and the original frequency, or the sampling time and the original period, that if I do that, I'm guaranteed to get a periodic answer? Yeah.
If the ratios are rational
the ratio is a rational number. Ooh, why would that even work? How to explain that to me?
Well, if the ratio is a rational number, that ratio.
Ratio of what now?
Sorry, the ratio of the original period.
Okay.
And of the sampling size is a rational number.
Oh, so if let me say that a different way.
Okay.
If one period of the original waveform was an exact integer number of samples,
Yes.
that would work.
Yes.
That would work. But you're looking at me skeptically, like I took something away from what you said, and you're right. Okay, but I simplified it. We're okay. So let's start there. Let's start with, and everybody's okay with that concept, right? You give me a waveform, and it's periodic, and if I have some integer number of samples that are exactly one period, then that's going to keep repeating on and on and on and on. We're okay with that, right? Okay. He's right, though. There's a more general case, but this one's easy to understand. So if one analog period is an exact number of samples, for sure that's going to work, right? So that's another way of saying we're using a sampling rate that's actually an integer multiple of the original frequency of the waveform. That's the frequency version of saying that. And for sure that's going to work, right? It's the original period. We get some number of samples, and that's one period, and the same number of samples gives me exactly another period, and on and on and on. That all works out great. So that works for sure, but he's right. That's not the only case that matters. There's more cases that are also fine. For instance, here's a 300 hertz sinusoidal signal, and I'm sampling it with exactly 3 samples per period. That's the case we're talking about. So 1, 2, 3, 1, 2, 3, 1, 2, 3. I get a repeating pattern. So here I've just taken these red dots where I'm sampling and done a connect the dots. And you might say I've changed the shape of the waveform, but I haven't changed its frequency. Both have the same fundamental period, right? This guy's got the same period that this does. All right. So that works, doing exactly some number of samples per period. That's fine. Here, I'm going to do 3.5 samples per period. And lo and behold, I do get a periodically repeating waveform. The period goes beyond one period of the original waveform. Because in 7 samples, exactly 7 samples, I get 2 periods. And that pattern repeats. Right? Likewise, use 3 what is that? 3 2/3 sample per period. Well, that still produces a periodically repeating pattern. Same thing happening over and over and over again. Because with this particular number of samples, I get exactly 11 samples in exactly 3 periods. So this was what he was getting at. If there's a relationship, an integer number of samples in an integer exact number of periods, that will also produce a periodic repeating waveform in the Discrete-Time version. Okay? So that's the gang, that's the rule. This, however, if I sampled with 2.236067 samples per period, you just square root of 5 times the tone frequency, you never get a periodic version, because I cannot define an integer number of periods of the original waveform that gives me an exact number of samples. And so I need a relationship between those two things in order to get a periodic result. And so if you're not sampling it at the proper rate, you get something that's not strictly periodic. Now, your book and several of them will call it almost periodic. I'm a digital guy. Well, mostly. It is or it isn't. It isn't. It's not periodic. what they mean by quasi-periodic or almost periodic is if you stand far enough away and kind of look at the shape, the envelope of it, yes, it's still a sinusoidal kind of thing, but the actual sample values do not match exactly. So it's got the right kind of shape, but it's not a periodic signal. So we're going to call it not. Okay. How do you make sure you get a periodic version? Well, he was onto it. We're going to compare, can we get a integer number of periods out of an integer number of samples? And so we want to get some integer multiple of our sample, of our analog periods. Well, analog periods capital T, let's let k be some integer value. That's got to be exactly some number of samples. Well, in time, t sub s is my sample time, and I multiply that by the period n. So these have to be equivalent. If that's true, then the period of the original waveform of the sampled signal is capital N, and that'll relate to k periods of the original waveform. Rearrange that as your textbook does. If these have to be equivalent, if we relate t sub s to the sampling rate and the period of the waveform to its fundamental frequency, replace the normalized frequency with the digital frequency, we find that if the digital frequency is a ratio of two integers, a rational fraction, k over n has to be a rational fraction. So if I can write the digital frequency as a ratio of two whole numbers, then my resulting signal is periodic. It's a mouthful for something that's actually pretty easy. So if I give you a discrete time signal, or give you an analog signal and a sampling rate, we can find the digital frequency by normalizing, or looking at the expression, say, oh, this is 30 hertz sampled at 75 hertz, make the ratio. This is 30 over 75. Well, even right there, that's a rational fraction. I know the resulting discrete time signal will be periodic. All right, so I know I can look at this combination of the original signal and the sampling rate and infer that. Okay. Or if you're working with not the original analog signal but the digital signal, just make sure you extract the discrete time frequency and ask again, can I relate that as a ratio of two whole numbers? If so, then you get a periodic discrete time signal. If they're not, you don't. Now, if you get that that ratio of two whole numbers, there's some value in reducing it as far as you can. Because if you reduce it to the lowest level possible, these two numbers have a significance. This is your k and your n. Right? This guy, that was k over n, when you do it, that's the number of periods in the original analog signal that your periodicity is covering. And this is your k, the number of samples in the discrete time signal's repeating pattern. Right? So this is your discrete time period. This is how many analog periods that represents. So in this case, n was 5, so get 5 samples, covers 2 analog periods. That was rough. So if I take x of t, that's cosine 2t, sample it at 10 hertz, do I get a periodic signal? You want to check that one out in your notes? Let me know what you come up with. Find the find the discrete time frequency, see if you can express that as a ratio of rational whole numbers to get a rational fraction. And if so, reduce it to find the period. So what's the analog frequency? 1 over pi. Uh-oh. And if we sample at 10 hertz, then the digital frequency is 1 over 10 pi. Is there any way to make 1 over 10 pi a rational fraction? No. So this would be a case where I sample a perfectly valid signal, but the answer is not periodic, can't be. If I said cosine 2 pi t, we'd be okay. Right? See how that works? Questions? Okay. One more step. How about this one? Oh, well, e to the j 4 pi t, sampled at 20 hertz. Oh, no. There's a e to the j up there. Oilers. What is that? Tell me what this is in cosines and sines. Cosine 4 pi t plus j sine 4 pi t. All right. Is that a periodic signal? Sure. This just happens to be complex. Its real part is periodic. Its imaginary part is periodic. And they both have to be periodic at the same frequency. That's cool. That's fine. Or a little. Okay. So it has a frequency of 2 hertz, right? And I'm sampling it at 20 hertz. Do I get a periodic answer? And what is the frequency? 2 over 20? What's the, or 1/10, what's the, how many samples in the discrete time signal for one cycle, one period? 10, right? It is a rational fraction, so we get a periodic sampled result. And when we reduce it, we have 10 samples in the discrete time signal that's in one period, and they happen to correspond to just one period of the original waveform as well. Okay, so 10 samples, one analog period, and there you go. Now I'll throw one more complication at you that's going to send you back to the 228 days. When we were doing Fourier series, we were working with particular frequencies that were harmonically related, that were integer multiples of each other. And before we got into there, we were looking at maybe what happens when you combine periodic signals of different frequencies, maybe harmonically related, maybe not. And there were some cases where if I combined 2 harmonic signals with different frequencies, that I didn't necessarily get a periodic signal as a result when I added them together. Oh, that's really old stuff. So, for example, there's a cosine and a sine with 2 different frequencies. If I add these together without sampling, we're just going to keep them in the continuous domain, the resulting signal is going to may or may not be periodic. Right? And if we want to figure out if it is and if what that period would be, well, we would what do we do? We'd find their frequencies or their periods, and then there was a, what is it, greatest common divisor, least common multiple thing we had to do. Right? Find the greatest common divisor of those 2, and it turns out to be 10. And so these 2 would actually combine to create a periodic signal whose periodicity had a fundamental frequency of 10 hertz, which was lower than the fundamental frequencies of either of those, but that's fine. Or if we think of periods, well, one has a period of 1/20th of a second, the other 1/30th of a second. We use the least common multiple of the periods to find the common period of the combination, or 1/10th of a second, which has the same reciprocal as that. So in the continuous time world, these are okay. I can combine these 2 signals, I get a periodic version, and we can predict the period and frequency of their fundamental frequency. What about if I sample them? Well, to get a periodic signal out of this combination, I need to satisfy a couple things. Each of these guys has to produce a periodic signal when it's sampled, and we have to already know that the combination in the continuous time world was also periodic. We've satisfied the first requirement. If we check these guys out, well, let's normalize the 20 hertz signal and the 30 hertz signal by the sampling rate, 20/70, and well, even right there we see that the digital frequency of each of these is a rational fraction, a rational function. And so those are okay. And we can apply the same mathematics to the discrete time frequencies and discrete time periods to figure out the new fundamental discrete time frequency or period. Here, this one comes out to be 20/75 or 4/15. That's its k over n. This one is 30/75 or 2/5. That's its k over n. So the number of samples in one period of this is 15. The number of samples in one period of this one is 5. We find their least common multiple, and that happens to be 15. So the combination will have a periodicity that has a period of 15. So we're applying this. Oops, I'll leave that there for you for a second. So same methodology applies, but I have to make sure each of these individually was okay with becoming periodic. If they were, then I could define a fundamental period for that new discrete time version. All right. Let's get to something a little more interesting, a little more fun. Let's ask the question in the last 10 minutes, how can we sample our continuous time signal so that we don't lose any information? Now, if I sample a signal and I don't get a periodic answer, is that going to lose any information? Not necessarily. I might not lose anything. I might be still okay. But there is some ways that I can sample a continuous time signal and actually lose some of its fundamental characteristics. We don't want to do that. Again, here's a discrete time signal processing system. We have a continuous time signal in. We do an analog to digital conversion to get to a discrete time signal. We're going to process that with some algorithms, with some linear systems. We're going to have an output discrete time signal that we're going to turn back into a continuous time system, or excuse me, continuous time signal. What we want to pose as a problem now is, while we're going to spend most of the quarter talking about what goes on in the green box, right now we just want to make sure we do this right and do this right, okay, so that the stuff I do in here is meaningful. And what we're saying now is what's important to me is this signal has information that's coming in, has some essential characteristics. When I take samples of it, I want to preserve those characteristics, those basic information that's carrying. I may modify it later, but I don't want to lose it in this step. So if I replace my green box with a wire, give it a transfer function of a 1 or a frequency response 1 everywhere, which is a piece of wire, let's just sample the signal and spit it back out. I'm doing a good job if this signal looks exactly like that one, right? That would be perfect. Well, I'll be happy if y of t didn't lose any information compared to x of t. Looks pretty much the same in any way that's important. And can I mess up this just by the sampling process? The answer is, I want what goes in to be what comes out without any essential change. What could possibly go wrong? Well, answer, lots of things can go wrong. And so before we do anything else, we've got to do sampling right. And what does doing sampling right mean? Well, okay, here's our 300 hertz tone again. And again, I'm going to sample it at some fixed sampling rate, which gives me the little red dots in this waveform that I just do connect the dot kind of plot here. And if you look at that plot, compare the top and the bottom, and I'm going to stand over here. You guys in the close up there are going to tell me, I changed it. The shape is different, right? One's sinusoidal, it's nice and round. The other's jaggedy, triangular. And I'm going to say, is my discrete time signal hat on? I'm okay. I'm okay with that. You changed the shape a little bit, but you didn't change the frequency. The period of that red signal is the same as the period of the blue. and its amplitude is probably the same. Okay, so didn't lose anything. If I sample at 1.5 samples per period, and then look at those two waveforms, did I change its period? Does the discrete time version have the same frequency as the continuous time one? Same period. Now, number one, is the red one periodic? No. Is the red one periodic?
Yes.
Yes. Is it the same frequency?
No.
Higher or lower?
Lower.
Lower frequency. If it's still periodic, I have an integer number of periods of the original waveform make up one period of this, so it's still periodic, but the frequency changed. Am I allowed to change the frequency of a signal in a linear system? Is that permitted? No! You're not supposed to do that. Linear system, no can do that. Linear system, the only thing it can do cosine. Make it bigger, smaller, make it shifty. Nothing else. No span, no contract, none of that. Can't do it, not linear. Sampling could be a nonlinear operation if you don't do it right. You can mess everything up at the beginning. Not good, not good. Let's try it again. Here you go. I'm sampling at 1.1 samples per period. Bada boom, bada bing, bada boom, bada boom, bada boom, bada boom. Completely periodic. Beautiful sinusoidal waveform of a completely wrong frequency. But it's sampled, and it's still periodic. So if you don't sample often enough, then the harmonic content, the frequency stuff in your signal moves, goes somewhere else where it's not supposed to be. That's not a good thing. That's a nonlinear operation. Yeah?
Is there a way to determine if you're sampling frequently enough?
Yes, there is. And we're going to have to wait till Friday to find that out. But yes. But this is not good. You cannot do this. Not allowed. This is what you don't want to happen. This is what we call aliasing. What is aliasing? Aliasing is shifting some frequency in the signal to a different location in the digital frequency domain, and it happens because you didn't sample often enough to see all the frequencies that were in there properly. And it's an irreversible process. Once I do this, I have no way of knowing this was the original signal. I just have a collection of samples that look perfectly good to me. I have no way of knowing I blew it. I don't know what the original, it's gone. The information's gone. It's non-recoverable. It's non-reversible. So it's nonlinear and non-reversible. You're done. So we don't want this to happen. What is the effect of that? Well, suddenly everything becomes ambiguous. You can't trust what frequencies are showing up anymore if you can't trust your sampling process. You've lost some information. The frequency, the very fundamental characteristic of that cosine is gone. Well, it's not gone. It's somewhere else it's not supposed to be. It moved. You audio people would consider this a distortion, and when we get to the modeling, it'll actually play for you the effect that it has on music. But we can kind of see that right now with the 3 minutes we have left. Let me show you what that's like. Okay, so what's going on there? Same picture we had before, and what I'm doing is we're creating these two waveforms, and then through the audio processing in the laptop, we're playing this signal and all of its samples, and then playing this signal and all of its samples. And so that was the two tones you just heard. Everything's hunky-dory, right? Same signal, basically. All right. If we sample a little bit slower, and a little bit slower, and a little bit slower, we'll keep going. In this case, we're still getting periodic results. The periodicity is spreading out, but it's still getting the right results. And if we go down to this, where I'm getting 2 samples every period, I still appear to have the same frequency. Right? And if we played those two back, same signal. Now, drop the sampling rate. Uh-oh. And drop it some more. Uh-oh. It's moving. It's dropping. And so on and so on and so on until you can, you know, as we saw before, go back, come on. You can bring it down to where it gets ridiculous, and you can't too slow for even the audio processor to play. And if you do something as foolish as sampling one sample per cycle, there's your samples. All right. So here's a clue, here's a hint that's going to bridge us to Friday, where we'll start talking about the theory behind sampling. You don't want to do this. You want to sample often enough to get all of the essential information, starting with preserving the frequency content of the signal, and Friday we'll look at how you do that. Check the online homework. There's some homework problems for next time. There is your first quiz that will be due before the next class, so make sure you hit on that.